I've been trying to make the point for a long time that 2D and 3D seismic imaging are complementary technologies. In this paper from 15 years ago, I tried to use an example of a photograph of a fish dinner to show 2D and 3D coverage and how they're kind of different and yet complementary. Fortunately, over the years, I came across a really excellent data set from Peru that illustrates this complementary nature of the two technologies on actual seismic data. So now what I want to show you is a field data example where 2D and 3D seismic data really show the complementary nature of the two technologies, where 2D seismic data has higher resolution in the shallow section, and 3D seismic data has a wide range of azimuths to illuminate below complex geologic structures. So here's the data set. We've got pre-sec depth migration of a 2D line across a 3D volume. And we've got tight spacing of the sources and receivers along a single azimuth that can image steep dips in complex fault geometry in the shallow section. In the 3D, these are 3D depth migrated traces extracted along the 2D line, and we've got strong coherency in the deep section below the overthrusts, where the source receiver azimuths were able to image below the complex geologic structure. Now we're having difficulty with the 3D depth migrated project, and we included some 2D depth migration lines in the project in order to get better near surface coverage. As you see, when we zoom in on here, we've got really excellent near surface reflectivity. We can follow these reflectors close to surface. We can tie the surface geology with a much higher pre-stack signal, so we can see move out on the gathers. We used Greg Cameron's AI method to help come up with the velocity model in this data zone and in the shallow section to improve the 3D depth migrated image. Because the 3D depth migration just doesn't have very much reflectivity in the shallow section, as you can see here. And it was even worse on the pre-stack gathers, where the signal quality is very low. And we'd have difficulty following these reflectors up to tie the surface geology. So if I flip back and forth, you can see the 2D is sharp and clear with very strong dips, and the 3D is very weak, noisy, and incoherent in the shallow section. So one might say, wow, why would you bother with the time and money involved in shooting 3D seismic data? But if we scroll down now and look into the deep section, then you can see where the 3D really shines, having multiple azimuths to image below this overthrusted structure and get this footwall features to come out in 3D, which we're just basically unable to image in 2D. The complex geologic structures and the ray bending and illumination issues, we really could never get much better reflectivity in the deep section than we see on the 2D line versus the 3D. So the complementary nature of these two technologies helps us to get a better, more complete interpretation of the subsurface, and we are able to use the 2D seismic data to get a much better velocity model and image a lot of these deeper reflectors with clarity. That's where I make the point where 2D seismic data and 3D seismic data are really complementary technologies that work well together in an integrated sense, in this case for the processing and also for the interpretation of subsurface structures.